We'll see what's going on with that in a few minutes. Okay, let me put this out of the way so I can get started here. I'm assuming that everybody got your homework done, that you took a look at the TTL inverter circuit, and you made sure you understood how that worked. And then you kind of extrapolated that into both the NAND gate and the NOR gate in order to understand how they might work at the basic transistor level. Does anybody have any questions? Frank?
I'm just making sure. The last class you said all these transistors are in a saturated state, correct?
Well, when they're turned on, they are. They're cut off when they're not operating. But yes, we operate between saturation and cutoff. Okay, let's grab one of these real quick. What's this one? And work our way through this one. So this is a standard NAND gate. Not very fancy, just TTL. We expect for our truth table. Where am I typing? Can't do that here. We have an A and a B input, a Y output, we'd expect it to be an AND function, which would be 0, 0, 0, 1, except for we're the inversion of that, we're a NAND. So we'd expect to find 1, 1, 1, 0 as the truth table for this thing. Now, if we look at this carefully and we simply omit input B, if we just say B doesn't exist, we have exactly the same picture we had for the inverter. Some of the numbers may be different, but it's basically the same circuit as an inverter. We'd have the same thing if we took A and got rid of it and left only B. We know that the one interesting state we have is right here, where both of the inputs are 1. So let's do that guy first. We'll set both our inputs equal to 5 volts. Then we'll look at this transistor to determine whether or not it's on or not at this point. Numar, is that on, the transistor on or off right now?
It's on.
Does everybody agree with him? Okay, so if we put 5 volts here, what we're saying is we can take and get from 5 volts current flowing. Seems to me if it's 5 volts on both ends, current would not be flowing.
Oh, sorry. So it's not on.
So if the transistor is off, and we can say that for both the inputs, then we know that this point right here has not been pulled to ground, which would happen if this was on. Since it's not pulled to ground, we have a path from 5 volts to the base of this transistor. Matthew, is that on or off?
Q2 would be on.
Because we can pull current from 5 volts through the transistor That should turn this transistor on.
Mhm.
Now, if it's on, one of the things we know that's going to have to happen here is this transistor is going to basically have as its collector and emitter the same value. So we'll have to remember that just for facts to know and tell. So this transistor is off. This transistor is on. What's the state of this transistor right here? Okay, because we brought this voltage down, and in order for this to be on, we'd need to be at least 2 diodes higher. And what we would expect is, in this case right now, for this transistor to be off. We don't have sufficient current, or voltage, I should say. We don't have sufficient voltage at this point to turn this on, which means nothing is going to be coming out of the pin. Instead, this guy, who, if you look at the 5 volts, has been divided into 1.6, 1K, a voltage which is going to be high enough that the base will be able to be 0.7 volts, turning this transistor on. If this transistor is on, that transistor is off. That means current can flow into the Y input and will be flowing in there as a value of 0, because if this is on, the top of the transistor is 0 as well, because we've saturated the transistor. And so we've basically demonstrated that this works exactly like the inverter when the inverter has a 1 on its input. We don't have to do anything else with this transistor because either or both are going to force the transistor to be off. Now, if we have one on, say B was on, now we do have a path from 5 volts through the transistor, meaning this transistor would no longer be off, it would be on. Because it's on, this pot here becomes 0, turning this off. And if that's off, this transistor can get biased by current flowing that way, turning it on. And we allow current to flow out of the transistor. This guy being off, of course, because we've taken and gotten this guy turned off, which means there's no way for him to get current. And so it operates again in the mixed state, and it's going to give us a 1. Now we know if we reverse A and B, same thing will happen. And if both of these are zeros, then we know for sure that there's no question that even if we didn't really understand the double emitter, that it would be turned on. We could do the same thing with a NAND, or with the NOR gate, but the NOR gate's basically the same as the inverter in parallel with itself. There's not a lot to be seen there. Now, some of you need to do some work on that. It doesn't sound like you did your homework. I'm not going to collect it because there's no point in just punishing those people that didn't do it, because they're going to have to do this fairly soon anyway, where it'll count for points. And if you didn't do your work, you're going to get behind really quickly. Anybody have any other questions about the TTL circuitry? Second?
Professor, just for the 0, case, it will be the same thing, right?
0, 0 be the same as this, because
Same
in
as
this
this, right.
case, the emitter, both the emitters are grounded,
Yeah, and we'll
which
be
means
on.
we can get 0.7 because we have a path back to 5 volts.
Yeah. Okay. Thank you.
Okay. Okay, let's think about a different problem for a second. Okay. Let's assume for a second that we have a TTL gate. This is just one of the 4 gates inside of the chip. It's a NAND. And we want to turn on an LED. So let's think about that problem for a second. We have 2 places we could hook the LED. One, we could put a resistor, and then we could have the LED sitting here to ground. The second case, we could have a resistor, and we could have the LED up here hooked to 5 volts. Okay. Anybody want to tell me what's good about one, what's good about the other one, what's good about both or bad about both? Anybody want to raise your hand? And these are LEDs. I didn't draw the little lightning bolts. I'll draw them just because they look so nice. Scott, what do you think?
All right, that one on the left, we're going to be kind of close. We're going to be cutting it close with lighting it when we want to, because the output from the gate will be, it'll be at least 2.4 volts. Actually, I'm kind of talking myself out of what I was originally thinking. I was trying to think if we were going to guarantee enough voltage to light the LED here. It looks like we actually would here. We would definitely have our 2.4 volts if we have the output of the AND gate on. So actually, I think this does work. I was thinking it might not, but it actually looks like we'll be okay because we need to drop 2.1 across the LED. It looks like we will here.
Okay, so what you're proposing to us is, since we've got 2.4 volts going across the LED, and we're going to drop 2.1 volts across the LED, that leaves us 0.3 volts or 300 millivolts to drop across the resistor.
Yeah, we should be able to design a circuit that'll do this.
Okay, does anybody disagree with that? Put your hand up if you disagree. Okay, well, in the data I gave you, or on the data sheet, was 2.4 the value? What's the name of that value for this output? Should be V output low, right? Or V output high, one of those two. We're assuming this is the high voltage. For our data, the data we had is 2.4 volts. What's in the data sheet? Just pop your hand up real quick once you look it up. I don't have my data sheet handy. Robert?
Yeah,
Is VOH 2.4?
Yeah, it's 2.4 minimum, 3.4 typical.
Okay, so it could be higher than this.
Right.
Now, the other thing we need to know is when it's high, How much current can we supply out of an output? Look it up, put your hand up if you know the answer to that one. Andrew, what do you think?
It was 0.4 amps max.
0.4 amps? That seems a little high.
Or 400 microamps.
Yeah, it's 400 microamps. So we can be supplied 400 microamps. How much do we need to light the LED? Robert?
Was it? We're still operating off 15 to 25 million.
Right, so the
right?
minimum is 15 milliamps. So do you see everybody see the problem here? His thinking was very good. We just need to think about each of the items in turn. So at 2.4 volts, which is when it's high, and we have to have high because of the direction we pointed the LED. We pointed it toward ground. Now let's look at the other case where we are hooked to 5 volts externally, and we're going to have 2.1 dropped here, 2.9 dropped here, and the current is going to flow that direction. Okay, how about this design? Does this one work? Stephen?
Wouldn't it blow out the LED? Or like burn it out?
Well, I see 2.1 volts. That's what we've been using all along.
Oh, okay. I just thought because you're putting 5 volts through.
Well, 5 volts doesn't move.
Oh,
5
okay,
volts
okay.
stays right where it is. When we ground this, which is when this would be turned on, what value is V output low? Scott?
It's 0.4 volts maximum.
Okay. So if this can go down to 400 millivolts here, then we still are going to get a drop. It's just not going to be 2.9, right? We're just going to take 0.4 off of this. And what's happening is going in and through that last transistor, there's no resistance. If you remember the picture of the gate, that simply goes to ground when it's a 0. So this is an attempt to turn it on when the 0 is asserted on the output. This is an attempt to turn it on when a 1 is asserted on the output. Design-wise, they both look okay. This one fails because of the fact we don't have enough current. How about this guy here? How much current is he going to allow coming in? What is IOL? Samir?
Is it 16 milliamps?
16 milliamps. Okay, is this high enough? Robert?
Yes.
Well, it's above our 15 milliamps. It's below our 25. I'll give you a little bit of a clue that if we do our resistor thing where we're 10%, but we're 10% the wrong direction, we may have enough, we may not. So this is right on the edge of being able to be used. So neither of these two designs at this point are reasonable to use. So if we needed to turn on an LED to reflect the status of a TTL output, we don't really have a good option. There's nothing in hooking an LED up to this that's going to allow us to do that easily. What might we do? Okay, Robert, what?
I can't remember exactly which it was, but wasn't there a circuit or a way that we could boost, where we could amplify the current?
Well, we've talked about one circuit that does that quite a bit. Dante, what is it?
Oh, I don't think I remember the circuit. I was going to say, couldn't we lower resistance?
Well, all that will do is increase the current. We still need to drop 2.1 volts across this, and we still have to because the LED won't light up with less than 15 milliamps. So this is right on the edge. This would not be a design that would be acceptable. We would want it to be closer to 20, just absolutely minimum, and more like we'd want it to be able to have maybe 30 milliamps or something, so we knew we had plenty, which we then could use a resistor to, burn up, basically. Well, the natural thing that most people come up with after looking at this for a while is, why don't we use a transistor on the output? So that when we come out of our gate, and this could be any type of gate, this would be where there's a base resistor, and then we'd have a transistor sitting here. That would be just like our transistor we've been using all along. It would have a resistor, it would have an LED, it would have some sort of battery. And we'd basically control through this resistor using this gate, this transistor. And that looks on the surface to be pretty good. I say on the surface because it turns out it really isn't as good as we want it to be. But it kind of does what we were talking about when we were doing our circuits a couple weeks ago. We replaced the battery on this side with a gate. So it provides a power, it doesn't provide power. So voltage, no voltage. The problem we have with it is this can produce as low as 2.4 volts, meaning that's our on voltage. It also can go as high as, I believe it's 0.4 volts in the other direction. Now, because this is kind of clipped off at 0.4 volts, we're safe. If this were a higher number, we'd be in trouble because remember, we have to be able to drop 0.7 across the transistor and still have some left for the resistor. So if this had been 0.8, which the inputs can tolerate, we could have been in some trouble. Because it's 0.4, we could make it work. More likely what we would do is we would say that we're going to amplify the 400 microamps that can pass this way. By saturating the transistor and creating a current on this side, which was approximately 15 milliamps. I think we've been using 20 as our average, 20 milliamps. And that way, by turning this on and off, we would get 20 milliamps or we'd not get 20 milliamps, meaning the light could be turned on or off using the transistor, but we're using the output of the transistor to do that. Now, the only real concern that most people would have with the design is we're using the 400 microamps to control the transistor. Wouldn't it be nice if we could use the 16 milliamps instead to control the transistor? Because then we'd have a little better granularity of control over here. So we didn't talk about in here the opposite of this transistor. We're using what's called an NPN transistor. If we really wanted to do this right, we would consider using a PNP transistor. Now, we're not going to study those right now, but just be advised that we could get the job done with an NPN. A lot of people do. You see a lot of projects online where they use an NPN transistor, and they're not really thinking very carefully because we're right borderline on not being able to do this because of this 0.4 volt value we could get for ground. So a little more designing would have to go on. But just for a practical purpose, for Halloween, in order to light up the monkey's nose, we could make that work. This circuit has the LED. This controls it from a gate. And we control the gate maybe with some switches or something. So just be advised that, you know, one sitting in the wild, if you ever see one directly controlling an LED and it's TTL, remember we're talking now about the characteristics of TTL, not some other technology. But be concerned that the design may not be a good sound design. Usually you're not going to be seeing TTL these days, but a lot of old projects still exist and all the parts are still available. So you could run across one if you tried to build something sometime. Just remember our discussion tonight. Anybody have any questions about that? Okay, let me make this disappear for a second. And let us move ahead. You have a question, Mikhail?
Yeah, I was gonna ask why 0.4 volts is sometimes enough and sometimes not enough to make it work.
Well, 0.4 volts in this case only makes it work because we need 0.7 volts across the base emitter. And we know that's what we're going to get. All the transistor problems we've worked have had 0.7 volts. 0.4 is less than 0.7, so even though it's only got a 0.3 volt margin, it would be okay to have that as our ground signal. It's still low enough that we can get 0.7 relative to ground. Because on the other side of the circuit, we would be using 0 because we're using a separate power supply. In other cases, if the number is too big, the 0.4 we had a while ago was not that same 0.4. It was 0.4 micro or 400 400 microamps, which is the output that it's able to produce on a pen. And that's not enough. In that case, we have to have somewhere closer to 20, well, 15 minimum, but close to 20 milliamps. Okay, we're going to, over the next class, shift gears a bit because tonight we're going to start talking about what capacitors are and what a 555 timer does, which leads us into being able then to talk about sequential as opposed to combinational logic. We've been talking all along about Boolean algebra and the implementation of it using electrical circuits, where we've just made the assumption that when the inputs change, the outputs change right now. After a couple of minutes of thinking about it, we would know that that can't be true just because it takes time for electrons to move around, for current to flow. And because of that, even though we may be able to express something in Boolean algebra and actually be talking about what it will eventually get to, we have to control when we look, and we also have to be able to control when we're going to be able to change states relative to somebody looking at it. So we have the obligation to make sure we don't change states during a time period when somebody else might be considering the value we produced previously as being golden, because it may not be while we're changing it. And we'll talk about that with sequential logics and flip-flops and some of those other devices that go along with it. But tonight, to introduce that, I want to first of all talk about another component we haven't talked about, which is a capacitor. Now, again, I'm not going to go into a lot of the theory, and in a couple cases, I'm going to fib to you a little bit just to make it not be too uncomfortable. It gets kind of hard, kind of fast, if we have to do all the math that goes with it. So the math belongs in a different class, not this one, but you'll still be able to look and get the principles of it by us being able to talk about it. And as long as you don't get caught up on the, well, if I were to do that, I would have a wrong value. Yes, you might, because we're not going to do all the detailed arithmetic. So what we want to do, first of all, is just kind of go back for a second and think about what a resistor is in our circuit. We drew a resistor as being a little squiggly line like that. And we talked about being able to put it in a circuit and that it would have a relationship that says there might be a voltage drop across it. Could be zero, could be infinite. And there would then be a relationship between that voltage and any current that passes through it and its actual resistance value. The resistance value we're going to use is going to be measured in ohms. Just use a capital Greek omega. The voltage drop will be using V for volts. And the current will use an A for amperes. Now, in general, we've been talking about the steady state of all of this. The resistance doesn't change. The current through it doesn't change. The voltage on it doesn't change. If we needed to say, well, now it has a voltage of 10 volts, we would be introducing a new look at the circuit. We said now it contains 0 volts. We would have to look again. It's not as if we saw it change. We're looking at 2 different times. Sometimes when it has a value, a voltage of 5 volts, sometimes when it has a voltage of 10 volts, sometimes when it has a current of 100 milliamps, sometimes when it has a resistance of 100 ohms. But each of those snapshots is unique to itself. Now, along with this, we determined we could talk about power in watts, so power measured in watts, being equal to a relationship which could be current times the voltage. Current through, voltage across. And the voltage across would be the drop of the voltage, because there can't be a rise across a resistor unless you're going the opposite direction when you look at it. But it basically is looking at a point where there is a voltage, a point where there is another voltage, and between the two, there'll be a value. We think of it in the direction which it drops with most of the problems we've worked on so far. We might someday think about it the other way, but ultimately it becomes a voltage drop at the end of the day. Over here, we had Ohm's law, which said the voltage that was dropped is equal to the current in amps times the resistance in ohms. Now, this is an interesting component because it generates a power usage. The power usage we have is dissipated using heat. And it's a real thing. This is real. So if I hook up a circuit and it has a resistor It will be true that Ohm's law is true. It'll also be true that the power law is true, and that some form of heat has been generated which needs to be dissipated. If you don't dissipate it, you could burn up the component. You put it next to something that's flammable, you could cause it to catch fire, but it's a real thing. It's something that we could measure as a quantity. It actually is a measurable thing that we can express in watts. So this we've gotten pretty good at. Now it's a steady state thing, and it really doesn't matter what we're doing with the resistor. If we were to take and put a sine wave through a resistor in terms of voltage, where it just followed some sine wave, at every point in time along that sine wave, we would see a dropped version of it in phase with it at the other end of the resistor. And it would follow Ohm's law, and it would follow a power law. And if we were to take over time and look at it and add all those up, kind of integrate it, we find that the power drop was indeed, a linear thing. And it was in phase with the voltage across the resistor, meaning that we're generating power as the resistance goes up and as the resistance comes down, because we'll be dropping less voltage, changing the current, changing the problem, the wattage will go down. Now, going up doesn't necessarily mean we're going to change the problem. I'm assuming we're changing other things as well. In general, as the resistance goes down, the current is going up, because to maintain the same voltage, if you reduce R, I has to go up. Now, I and V are the components of power. We, of course, could replace V here with IR, and then we have I squared R is what P is equal to. But notice that then the I gets a squared term. But nevertheless, it's all linear. It's all real. Really happens. So now we go along and we say, well, wonder what would happen if I took and I put a gap in the circuit where this side is going to get a higher voltage applied than this side. Well, we would have a break in the circuit. It would look like infinite resistance. It would look as though current cannot pass through this because there's a gap in between, and the current, unless it breaks down, can't get from one wire to the other. And that is true. Now, if I push these two plates closer and closer together, so that I have basically some metal, some insulation, and some metal, and then I provide high voltage relative to low voltage across it, and I wait 5 minutes and I look at it, I'll see no current passing through the device. It will appear to be infinite resistance. No matter how close together I get these, unless I put enough voltage to break down the insulation, which could happen, but the closer I get, as long as I keep the voltage under control, no current will pass, except for the fact that it turns out that if these are close together, at the time I first apply the voltage here, the other side, the other plate, will respond to it by generating some current. Now, it doesn't work exactly like that, so we're not going to get into the physics of it, but for the people that this would be hard for, this is a simple explanation. So basically, what's going to happen is, only when I have a change in current and voltage over here will I see a response to it on this side. So this is a capacitor. I just call it a cap. Capacitor can come in a couple flavors. One of them is the picture I drew here, which is, it's called polarized, meaning it matters which side I hook to the positive. Many, many large value capacitors are polarized because they're easier to make that way. And they will basically, I won't say blow up because it sounds violent, but sometimes it is. They'll basically destroy themselves if you hook the positive to the wrong end. You may see them drawn like this with no curved side. But when you do see a curved side, it's the negative side. Unlike almost every other device we draw, when the flat side is the negative, in a capacitor, the curved side will be the negative side, and the flat side will be the positive side. If it's polarized, there'll be a plus sign next to the flat side. Now, since current can pass through this, when it's passing, we would think that we would be following Ohm's law. Turns out that that's not exactly what's going to happen for us. Rather, there's going to be something which is time dependent, which will tell us what the capacitor is going to do. Additionally, because we could still apply a power formula, it's going to generate some power. The power, however, is not real. The power is imaginary. I just write out imag here for us. So the power it generates, if we were talking to the power company, they wouldn't be billing us for it unless they happened to know we were a large company and we were doing this to bypass paying our bill. But they would be charging us for this. Here we're using voltage and current to generate real working power because it generates heat. Here we're generating imaginary power, which does not generate heat. This won't work for us, but it exists. Now, a capacitor has some rules and things that we're going to think about later, but basically, we're going to say the voltage lags the current. So while we can change the current that it looks like passing through this capacitor quickly, depending on the size of the capacitor, it's going to respond to the changes in current by changing its voltage difference more slowly. Now we can actually, if it's pure current and pure voltage, we can, and the phase difference is exactly 90 degrees. We can talk about sine waves and cosine waves all day. We won't. We just want to think about this as resistant to changes in voltage. It doesn't want the voltage on it to change. Now, there is a secondary device that we're not going to talk much about, which is basically a coil. It's called an inductor. I'll just put IND here for it. The inductor is kind of the counterpart of this, but its current lags its voltage. What that means is once you get current starting through this, the coil generates a magnetic field, and the magnetic field will prevent the current from changing. Just like up here, the capacitor's ability to store the voltage and the volts that have on it is slow to change because it resists changes in voltage. This resists changes in current. Now, why do I tell you that? Because it also generates imaginary power. We won't talk about them too much after tonight, but if we ever do anything with a motor, or we have anything like a solenoid or something like that that has a coil, or if we were building a receiver for an antenna where we have to balance the amount of capacitance and inductance in a circuit. These don't really have what we would call a resistance. Instead of a resistance, we're going to use the word reactance. So a capacitor has reactance. An inductor has reactance. And they're the imaginary versions of resistance. So let's look at the complex number plane for a second here. In a complex number, which we might list like 100 minus J50. That's equal to some complex number over here, X. This is the real part. This is the imaginary part. Now, electricians use the letter J where mathematicians use the letter I. And the reason is just not to get confused with current being a lowercase I. But you'll see J in most math problems that involve electronics. So this is a number which we call the impedance of a particular set of elements. The impedance is a complex number with a real part. The real part is called the resistance. And the imaginary part is called the reactance. Now, on the complex number plane, if I have something that's a pure resistance, which is all we've been working with so far, it lies right along that axis. So if we got a 10K ohm resistor, this line would be 10,000 long. We got a 100K ohm resistor, that's 100 long. Now, if we don't have any resistance, but we have pure inductive reactance, it'll stick straight up. Purely plus J, some number measured in ohms. So a reactance of 100 ohms would look like that. The reactance of a capacitance, if all you have is a capacitor, points straight down. Its reactance looks like minus J50 or something. It's measured in ohms, and it's the imaginary part in the negative direction. Now, if we have a circuit which has some inductance and resistance, which we can measure, what we're going to do is we're going to look at what value the actual impedance of that particular circuit is. We also might have capacitance in our circuit. If we have capacitance in the circuit, and in this case, this guy's a little longer than him, we're going to wind up with a vector which says we have more positive than negative impedance. So we'd have a plus J on it. We're still working with reactance there because it's only the right-hand half of the complex number. Now, if we wanted to combine this with that, we would once again do a vector addition of that. And just take, if we hook the end of this to that, and we go straight forward, we come back down, we go back, and we get a line that goes out to this. This line, which is the vector sum of that, becomes the impedance of that circuit. Again, it's mostly inductive in this case. Now, we are going to be working mostly with capacitance. So most of the circuits we see will have some resistance, some capacitance, where we can take and find the impedance of it being the vector sum of the two. And this would be whatever this number is here. Say it's 100 ohms. Minus J, and whatever distance this is. Here, let's say that was 50 ohms of reactance. And then this number here becomes the impedance, the whole thing is in ohms, of a circuit which has a 100 ohm resistor and a, in this case, 50 ohm reactance. So what we need to see is how do you derive a number like reactance from a capacitor? Okay, first of all, capacitor is measured in ohms. I'm sorry, not ohms, farads, named after Faraday. Now, there's a little messy thing that goes on with these. For example, do you remember that if we had this number, let's actually write some of these numbers down. Somebody tell me how we would verbalize that particular measurement there. Frank?
That would be 1 times 10 to the third power.
Yeah, well, let's put a unit on it. Let's say we're using farads. So what would we say?
I actually meant to the negative third power. 1 times 10 to the negative third power farads.
Okay, so how would we say that? Scott?
1 millifarad.
Yeah, except for with capacitors, this is the tricky part. Instead, we would say 1,000 microfarad. A little odd, but that's what we would do. The second guy, we would say 100 microfarad. The next guy, what do you think it's going to be? What do you think, Dante?
Would that be 0.1 microfarad?
Yeah, you've caught on here. When we're talking about capacitors, a farad is a pretty large unit. It turns out that most of the capacitors we talk about are expressible as something that's kind of microfarad looking, or picofarad. The British use nanofarad rather much, but we don't. Most of the capacitance we deal with are expressible as microfarad, even though they'll break some of our other laws, and as picofarad. So things in the nanofarad range are going to be, so this would be 100. This guy is going to be done as 0.1 microfarad. He's going to be called 0.01 microfarad. he's going to be called either 0.001 microfarad or 1,000 picofarad. And pico, then the next set of three, they would be 110 or 1. And we just, it's like we've jumped over the millifarads and we jumped over the nanofarads. But that's, you'll get that right if you see it. It's not that hard to catch on to it. And again, farads are fairly large quantities, so we're not as likely to encounter them unless we're using the larger battery type things that have been used in the past 10 years where we've started to use them for other purposes. Now, if we were to look at a capacitor in a circuit and we provided a steady voltage to it, what we're going to basically see is no voltage on the other side of the capacitor. If, however, we gave it a sine wave that's constantly changing, we're going to see something that looks like a sine wave on the other side of the capacitor, but it's going to be out of phase with the sine wave. Because while this is able to change, remember voltage on the capacitor is slow to change. So if we were measuring the voltage we see we were applying, which is going to be basically a current, which should then change the thing, this looking like a sine could look like a cosine wave, for example, on the other side. We're not going to do the math to worry about what it will be. And in general, we don't have pure sines and cosines coming at us anyway. But just be aware that what comes on the other side is a result of what we have applied to this side. And you go, okay, so what? All this sounds like a lot of so what to me. What could we possibly do with a capacitor that's going to be helpful? Because right now they sound like they're aggravating. Well, let's take a look for a second here. Let's assume for a second that I take a capacitor, a resistor, and I put it so that it sits like this in a circuit. And what I'm going to do is I'm going to apply some sort of a waveform right here, which will be seen across this at the top of the capacitor. And then we can actually look at the top of the capacitor by measuring over here what we're looking at. I'll ground that. Now let's imagine for a second that I'm going to put 5 volts on this. So we'll say this is 5 volts. And I'm just going to maintain the 5 volts. And let's assume, just for the sake of argument, that I didn't do it at this exact instant, but I did it about 10 minutes ago. And I come back in and I look at my circuit. Well, if I put 5 volts here, there'll be a drop of some sort across the resistor. And I'm going to see some voltage here, which is basically the 5 volts minus the drop we have here. So it's a little bit less than 5 volts. Now let's assume now that I drop this to 0 volts. It's no longer 5, it's now 0. Well, what's going to happen right here? Well, this had 5 volts and there was a little bit of a drop here. But doesn't that mean that the top of this capacitor must have also been 5 volts? Sure it does. I said we're going to come back in a while. In a while, if this is less than 5 volts, this will be whatever that number is. But if I drop this to 0 volts, shouldn't I see this drop and then this go? Well, we can't go negative because we don't have anything that will supply negative voltage, but this could go to 0 with no voltage drop across this. So when I drop this, what I suspect will happen is this capacitor is going to slowly start losing whatever voltage it had. It could go either way. It could be stuff over here, but let's pretend like there's not for the moment. And over time, it will drain itself down to having 0 volts across it. And then I'm going to put this back to 5 volts. And we can imagine or envision that this is going to start charging. And after some amount of time, this will have 5 volts on top of it. But once it stops, this stops changing, the voltage here can't get through to ground. So it's just going to be whatever that voltage is. Everybody, give me a green circle if that kind of makes a little sense. That didn't make a lot, just a little. If this were a bucket and I was squirting water across the floor, but water would go in the bucket. If I dried this off, eventually this would evaporate and all the water would be gone. Okay, well, that's kind of what's going on here with this, is that if I start this, this capacitor will charge to whatever voltage I'm giving it, because then it's going to stop charging. When it stops charging, this will see all the voltage. But that means the whole time, I'm going to put a big eyeball here, whoever was looking right here didn't immediately see 5 volts. And they didn't immediately see ground. Instead, there was some sort of a delay introduced. And the delay must have been some sort of a function of the changing voltage here. So what we need to know is, how do we determine what the time constant is? Basically, how long does it take this to charge or discharge given a particular value for its capacitance? It's basically its reactance, but its capacitance. Let's pull down a sheet here. We go to our website. You can do this as well. / I think it's called time underscore constant dot GIF, GIF. Let me stick this on a notepad so you can copy it. And go ahead and download that, or at least bring it up so you can see it on your screen. Now, this chart has 2 things in it. One is the charge time of a capacitor, and the second is the discharge time of a capacitor. Notice along the bottom, we have 1, 2, 3, 4, 5 of these capital T things. T stands for time constant, but it normally would be called tau, T-A-U, the Greek letter T-A. Tau is what we actually call the time constant. Now, I'm going to write it here and then we'll go back to the other chart. It takes 5 tau to completely charge or discharge the capacitor. Keep that number 5 in your mind. So from the point where we start charging that capacitor in the last picture, after 1 tau, And tau, actually, I don't have a notepad there to write on, but it looks like a little squiggly top T. The thing will be charged up to 63% of its eventual charge amount. After 2 tau, it'll be 63% more, which is 85%. 3 tau, 95%. 4 tau, 98. And after 5 tau, it's not really 100, but it's as close to 100 as it's going to get. If we were discharging it, removing the current, it discharges 63% at the first tau, which is down to 37% of its final value, down to 15, down to 5, down to 2, and then finally down to 0 is the 5th tau. So what we need to know is how big is tau with a particular capacitor. Notice that right now, these are relative numbers. Does it have anything to do with the total amount of voltage? Well, nothing yet, because all we have is a percentage. So the time constant is equal to the resistance that we're going to be discharging or charging through in ohms times the capacitance in farads, and that will equal 1 tau in seconds. It's sometimes called the RC constant. So let's take a problem here. Let's say we had a 1K ohm resistor in our circuit in the last picture. And the resistor we had is going to be a 10 microfarad capacitor. So how many seconds is it going to take for us to charge our capacitor up to 63% of its final value? Get your calculator, grocery store calculator, and calculate that for me, and put your hand up when you get the answer. Gotta find my calculator. Probably left it at the grocery store. When you have a number, put your hand up. Okay, Andrew, what number did you get?
0.01 seconds.
Which is, how would we say that?
Is it 1 millisecond?
Would you say 0.01? Is this what you said, 0.01?
Yeah,
Seconds?
0.01 seconds.
How many milliseconds is that?
Is it 1?
Well, it would be through a group of 3, 0, 1, 0 would leave us with 10 milliseconds. Okay, let's do the math. Since some of you didn't complete the math, I'm assuming your calculator's too hard to use. Get a cheaper one. So we need 1,000 times 10 microfarad. So that's 0.00001. So we get 0.01. 0.01, which is 10 milliseconds. So after 10 milliseconds, our capacitor, given that resistor and that capacitance, will have charged 63% of its final value, meaning that if we were going to be charging it to 10 volts, it would have charged it to 6.3 volts in that amount of time. Notice carefully, in period, B period, notice bene, that it doesn't matter what the voltage is. Voltage is not part of the calculation, only when we say what's 63% of it. So it's not affected by the voltage you're charging to. The same amount will get charged in 1 T unit. So how long does it take to charge to 100%? Raise your hand if you know. Sam? Samir, I mean, I was looking at the wrong list there.
Is it 50 milliseconds?
Yeah, 50 milliseconds. Now, how long would it take to discharge completely if it started out at 100%? Robert?
Also 50 milliseconds?
Yeah, absolutely. It takes 5 time constants, or 5 tau. Okay. If we start at 10 volts, how long will it take to discharge to 1.5 volts? Raise your hand if you know. Gotta be more than those 2 guys that know the answer to this. Peter, what is it? Patricia, can you help him?
Is it still 15 milliseconds?
Well, we wanted to go down to 1.5 volts from 10 volts. So if we envision 10 volts being here, we'd be down to 3.7 here. We'd be down to 1.5 here, which is the number we want. So it takes 2 time constants. 2 times 0.01 is 0.02. So it would take 20 milliseconds. You guys are making me worry. I'm going to have to order some extra red pens from Amazon for this first test, I can tell. Don't want to have to do that. I like to have the nice big blue check marks instead of the big red X's. You need to be able to do this stuff. This is not hard. If this were hard, we wouldn't be doing it in this class. We'd be in my hard class, which we don't offer at Mercer this semester. Okay. Let's go back for a second. And let me configure this picture a different way as well. This is the picture we currently have in view, where this is the point of interest. Oops, didn't mean to do that. We're looking right there. Now, as a backdrop to remembering this, early on when we were talking about resistors, We put two resistors in a row right here. We said, here's plus 5 volts or something. I don't remember which voltage we used, any voltage. Here's ground. And basically, if we were going to determine the point right here, what the voltage is at that point, we'd look at the proportion of the values, and there were methods we had for determining what value would be here. We later took this same circuit and we bent it. And we said that if we were interested in this point right here to do something, what voltage would it be? And this might have been something resistive and this was resistive, but we cared about this point in the middle. Same thing here. These could be in a straight line or they could be bent like this, but the point we're interested in is the point in between. Now, just bear with me for a second here. This is going to change voltages slowly relative to current changes. And this is going to change voltages slowly relative to current changes. But the voltage in here is going to be a function of that change. If I didn't look at what was hooked up over here, but I just thought about current flowing through here or current flowing through here, they're basically the same circuit except for where the capacitor has been placed. And that makes a difference. This particular configuration, where I have the resistor before the capacitor and I'm looking between them, is something that we call a low-pass filter. This configuration down here, bet you can guess what it is a high-pass filter. Meaning that this, from here to here, even if you're passing very slow moving signals, like DC, where it doesn't change at all, we will see the result of that right here. And it'll basically be the same as though that signal coming in is filling this up like a bucket. And when it's finally full, basically anything passes through. The only thing that could cause that to change would be if we sped this up, uphill, or we slowed it down, a downhill type of voltage. We could control how much voltage is being maintained inside of this. Now, we might add to this something like a resistor in parallel to it with a high value that would basically, when no current was going into the bucket, would let it escape. But we won't worry about that right now. Just we know that this circuit could be made fancier. Down here, clearly, if we have direct current or just a signal that doesn't change, it can't get through the capacitor because capacitors only pass things while they're changing. So if we have a DC signal, nothing goes through. If, however, we have an alternating current signal, the higher it is, meaning the faster it's changing, the more likely it is to get through. Here, the slower it is, the more likely it is to get past this without getting the bucket filled by it. I dig a hole and I squirt a hose across it. The hose doesn't fill the hole if I let the hose point across the hole. It has to kind of dribble in a little bit to fill the hole up. In this case, it's like I have a solid wall and I'm knocking on it. If I knock once and don't knock again, you don't ever hear it. If I knock a bunch of times, the more I knock, the more you're going to hear it. These in practice actually have math functions they are performing. Anybody have an idea what mathematics function this is performing? Well, depending on whether or not you've had calculus, it might jump out at you or it might not. This circuit is performing integration. Meaning if I have a sine wave across time, it's going to fill the bucket, it's going to drain the bucket, fill the bucket, drain the bucket. It's basically going to integrate so that the area under the curve, high and low, offset each other. However, if I put a wave in that looks like this, which only goes up and then comes back down where this is 0 and this is some higher value, never goes negative, this value will wind up in the bucket and stay there until I drop it again and it integrates back to 0 again. So this is going to perform integration for us. Could be handy. This is going to do the opposite. It's going to do differentiation. Well, I can type that. It's going to do differentiation. A differentiation. I think I spelled that wrong, but it's close. It's going to take the derivative of the function that's coming in. So whatever function comes in here, we'll see the derivative of it right here. Now you might say, well, so what? How could that possibly be handy? Well, integration and low-pass filters go hand in hand in that if I were building my own bass guitar and I wanted to emphasize the low frequencies, I would have these circuits all over the place. If I wanted to make sure that some high frequency things got through and not the low frequency stuff, maybe 60 hertz hum from a power supply, I could use a low pass filter to let the signal go through. A typical example would be your TV remote. It has a low signal imposed on a 38 kilohertz infrared wave. 38 kilohertz we'd want to get through with a high pass filter, and then we'd want to decode it using a low pass filter to pull off what channel did he really want. So these come in handy in all sorts of venues. But here's one that could come in very handy for us. Let's assume that I have a waveform that does that. It goes up and then back down again fairly soon. If I have a high-pass filter, what I'm going to see on this side is at the exact time when it went up, I'm going to see a spike. The spike is going to be removed as soon as it doesn't change anymore. Doesn't change, spike, doesn't change. Then I'm going to get another spike going negative. So I can find the leading edge or trailing edge of some rectangular wave by taking the derivative of the function. And if you think about it, this kind of holds true. While it's here, that's a constant. What's the derivative of a constant? It's the number 0. What about when we get something that changes radically? Well, this is actually a high frequency event, and a spike value is the appropriate thing to see if you're looking for a derivative of that. What if I had a slowly rising signal? What I'd see in the derivative is where it's rising, I would see a constant value, which is non-zero during the time it's rising. So I can use this to actually differentiate a signal, which would come in very handy in lots of situations where I don't want to have just a single state coming out of my the bend in the value here. So keep these in mind as something that you're going to see. And then let's talk about the usefulness of that as we move forward. I think I've covered the theory part we need now. Let me just double check on this piece of paper here that there was nothing that was too left out. One of the things I didn't tell you back when we were talking about capacitors in general is they are frequency dependent. And if we were looking at the reactance, let's see, can I get that to Yeah, there we go. So if I wanted to compute the reactance of a particular capacitor, let's say I had a 0.01 microfarad capacitor, and I want to know what its reactance is, because remember, reactance is in ohms. How do I turn this into ohms? And remember that the ohms for reactance are imaginary. They're going to generate an imaginary power. They're not going to be the power that's going to generate heat. So to do this, we have a formula. The formula is 1 divided by little omega C. And that's equal to our capacitive reactance in ohms. And you go, well, that's great. I see the capacitance here, but what the heck is omega? Omega is basically what's called the angular frequency. We can simplify looking at it. We can rewrite this formula, expanding it. Two pi, which introduces radians, right? 2 pi times the frequency times the capacitance. Now we see if we stick an R in here also, we can generate where that where the pass filters, like the low pass and high pass filters, do the thing. But we don't want that in this formula. All we're going to do is we're going to say, what's the frequency we're operating at? Multiply that times 2 pi to turn it into radians, and that'll give us omega. So the angular frequency in omega, or in radians, is this value here, times the capacitance, will give us in ohms, once we invert it, will give us the reactance. So let's do this for our thing here. And you should have a quote. What is the question you should be asking me? Robert, what is it?
How do I know what the frequency is?
Exactly. What frequency are you interested in there? Well, let's take it at a couple of frequencies. Let's do it as though the frequency were 10 cycles per second, which is 10 hertz. And secondly, let's do it as if it were at 10K hertz. So work that, put your paw up in the air when you get an answer to both of them. Okay, let me do one with you and then you can do the other one. 2 pi f, so I'm going to take 2 times, what's pi? 3.14159 times the frequency, which is going to be, we'll do the top one, times 10 times this guy, 0.0000001, which equals that. And now we need to invert that. That's my inversion here. So if I did my arithmetic right, which I'm not sure I did, it looks like a big number. This is roughly 1.6 mega ohms. Let's write that down. You all were watching me to see if I did the right math. I'm not sure I did or not. Let's do it again with the other number. We need 2 times 3.14159 times, what did I say, 10,000? Times C, and we said capacitance here is 0.00000001 equals that, which we're going to invert. And this says it's about 1.6K. Anybody else do the math and see if you got the right same answer I did? I can make mistakes with typing up here easily enough because my keyboard's not where it should be. Now, this is the reactance of those two values, meaning that in my circuit, let's say I was doing this guy right here. Again, looking at this spot right there. If we're using the 10 hertz frequency, this is going to look like it's 1.6 mega ohms. So it's going to look huge. So at 10, what we need to do is we think about this as a circuit. There's going to be some value here, which we haven't included in the circuit because it's the thing that determines, you know, where the low pass and the high pass filter. Remember the R I told you we didn't write down. But you can only imagine that as this gets bigger and bigger and bigger, more voltage is dedicated to the capacitor, meaning that the output swing here is going to be a lot higher. Remember we said this is a low pass filter? Well, that showed that this low frequency passes very well. If we change this down here to being, we're going to put a frequency through that's 10K ohms, this number here is going to be divided by 1,000, right? So instead of that, it's now going to be just a 1.6 K ohm resistor, meaning that the significance of this got bigger and bigger and bigger. We're going to lose more across this than that, meaning the higher the frequency, the less signal gets through. So this behaved exactly like we would expect it to. And you'll need to play around with these a little bit before they make a lot of sense. Okay, let me just double check here that I didn't miss anything that was important for this class. That page looks okay. That page looks okay. Okay, let me clean this up just a little bit. Will I need this? I won't need that for a while, I don't think. Okay. One of the circuits that, or a circuit component that we're going to encounter along our travels is going to, actually, let me use this for that. It's going to be called a 555 precision timer. And it's a very common older chip. While it's not TTL, it plays nice. It also is very LED friendly. So we need to download the data sheet for it. And let me see, did I put that data sheet? I did. If you go to the lessons and you refresh there, you should see 555 timer data sheet. Give me a green light when you've got it. That's all the size they're going to give me. Okay, I'll live with that. Okay, everybody get that? Okay, everybody give me a green light right now. I want to see who's here and who's not. Okay. Okay, let's read the features. We can time from microseconds to hours. We can operate it as what's called an astable or a monostable multivibrator. Astable means that there are, well, I should say there is one state. Actually, I'm reading you wrong. Monostable says there's one state that is, when it goes to it, it wants to return back to the original state fairly easily. We can configure it so that is the state of operation. A second one is called astable, which is the one we'll probably be using mostly, which says that both states that it can assume will want to get back to the other state. And then finally, there's one called bistable, which is it's very stable in both states. And we'll talk about that next class using a different type of chip. It is TTL compatible. Notice, please, that it can sync or source. Sync means into the chip, source means out of the chip. Either 200 milliamps on this particular one. That's plenty to do our LED. We could do a lot of stuff with 200 milliamps. It is TTL compatible, so we'd be able to assume that if we operate it at 5 volts, that the inputs and outputs will work just fine with TTL. They give us a couple things, but these are just made up just because at the time that's what they were trying to sell a lot of. There's some text you may want to read on your own. We would be working out of a PDIP package, which we said last time is a plastic dual inline pin chip with 8 pins on it. And we'll talk about this internal schematic in a few minutes. Here's the thing view from the top. In this case, ground is the top left pin. Remember, there's a notch near pin 1. Pin 8 is directly across from it and it's voltage VCC. Trigger, number 2. Number 3 is the output. Number 4 is a reset, and reset is a reset going low, not high. We have a discharge pin, a threshold pin, and a control pin, if you want the real names of those. So it's ground, trigger, output, reset. VCC, discharge, threshold, control. And we can also buy it in other packages. They actually make a 556, which has two of these in the same package. It's also very common. Down here, there's a little discussion of whether it's input or output or how it would be used. Notice that the output pins, control can be either input or output depending on how we're using it. Generally, we'd leave it unconnected or bypassed for an astable multivibrator. Discharge is an output pin, and output is, of course, an output pin. The others that would be on our chip are going to either be input or, like VCC, they're going to be the input voltage. Since it's not TTL, we can operate it all the way up to 18 volts. So this has applications outside of computers and is commonly used for applications outside of computers as well. Many of the devices you get, sometimes the power brick you get with the device, if it's nonlinear, will use a 555 as a chopper circuit to give you something that looks like a square wave. The highest the input voltages can be for these four input voltages are whatever you chose VCC to be. So these can support 18 volts if you have 18 volts in. In our case, we put 5 in, so these can max out at 5 volts each. We don't worry about thermal impedance. That gets a little too much for this class. Or the temperature of the chip. We're not going to worry too much about that, which would include our storage temperatures and things like that. So operating, if we're using a 555 from these companies or this one, we want to use between 4.5 or 16 volts for the first three or 18 volts for this guy. Generally, we'll be down near the 4.5 because we would be using this with TTL. The output current can be plus or minus 200 milliamp. Some people forget that it can also be negative, meaning going into as opposed to out of the chip. And these guys, we should not exceed our VCC. So if we pick 16 or 18 for a chip, don't exceed that value. And finally, the characteristics of the pins. They are specific per pin, and we would check this data sheet. But we did learn that they are compatible with TTL. So if we just wire it up, we'll get voltages as long as we stay near 5 volts for VCC, which meet the requirements here. This is worth running your eyeballs over because there could be a test question about it. But you know how to find this page, and then it's just look it up. Okay, a lot of charts explaining the data you just saw. Then some description where this functional block diagram is going to come into play for us. Now, this is printed up elsewhere. If you go to the website and you download, I think I called it 555.png. Let's see. Yeah, you'll get that page. We're in the data sheet here. So let me see. Do I want to do it? Actually, I'm going to use the data sheet. No, I'm sorry. I'm not going to use the data sheet. I'm going to use the file so I can write on it. Where's my view pen there? View. Zoom out. There we go. Okay, so this is what's inside the chip. I'm not sure we're going to get through all the operation of this chip tonight. If we don't, we'll finish it on Wednesday, but we can certainly get through this diagram. Now, interestingly enough, there are two components on this page that we haven't studied and won't study until later in the semester. One we'll study next class, but the others we won't. So I'm going to just tell you what they do and let your imagination then fill in the details. A couple other notes about this. These three devices here, this one, and this one are just another way to draw a resistor. Instead of the squiggly line, just a little box like that can be used to show a resistor. We do have an indication here that reset goes to an inverted signal. That tells us that when reset goes low, it's going to apply a reset to this box, whatever this box does. Notice the trigger also is hooked to a negative signal, as well as this junction here between two resistors and control are hooked to an inverted signal. There's two other inversions over here that seem to wipe each other out. We'll talk about why later. Now let's talk about, I'm sipping some coffee here to see if it's really coffee. That's why I was quiet for a second, because it could have been anything. Let's look at this. All of the stuff you're looking at here, except for the labels, are inside the chip. So every component you hear or see here is inside the chip. None of it is outside. So we need to see what the chip is doing internally before we can actually figure out what it's doing externally. So let's start as simple as it gets, which is over here on the left, these three resistors. Notice that VCC on pin 8 is tied to one end of those resistors, and ground on pin 1 is tied to the other end. So VCC and these three resistors build a voltage divider. Unless we hook something up to control here, all three of these resistors will appear to have the same effect on the voltage. Let's assume for a second, and I'm going to use a number we wouldn't really use, but it just makes it simpler to look at, that we have 0 volts right here. And let's assume for a second that VCC is 6 volts. That means that if these resistors are equal, I will see 1/3 of VCC right here at that spot. And I'll see 2/3 of VCC right here. So the voltage at this spot right here, if this is 0 and that's 6, would be 2 volts. So it'd be 2 volts right there, and there'd be 4 volts right here. Now these devices that we have right here look a little bit like an inverter, except they have 2 inputs instead of 1. They are a device called an operational amplifier, or an op-amp. And what an op-amp does is very simple. It takes the voltage on the pin at the top, let's call that the plus pin, and the voltage on the bottom, which has been made basically a negative value, meaning we can subtract it, and then adds the two together. So whatever the threshold pin has on it, we subtract 4 volts from it, we'll get a number. Now, normally an operational amplifier is operated with what we call feedback, meaning a piece of the output is brought back to the beginning to make the math a little bit more scaled into a value. In our case, we have no feedback. I'm just going to write no FB. Because there's no feedback, we're operating as something called a comparator. It's one of the ways it can operate. Comparator. What a comparator does is it does the math just like an operational amplifier. But let's say this said 2 and this said 1. Well, that would be 2 minus 1 is equal to 1. An op amp would give us a 1 on the output. What a comparator is going to do is it's going to give us the voltage supply. So it will produce 6 volts if the top pin is bigger than the bottom pin. If the top pin is less than the bottom pin, it will give us 0 volts. So it can only give us 2 outputs, fully on, fully off. And it's comparing, in this case, to see if the plus pin is bigger than the minus pin. Same thing down here. If the plus pin is bigger than the minus pin, this will put full output. It's a comparator. If the top pin is less than the bottom pin, it'll give us a 0 out. So this is a comparator. Now let's assume for a second that the trigger pin has 1 volt on it. What's the arithmetic being done right here? Who can tell me? Scott, what would it be?
So we're going to be comparing plus 2 volts in to the minus 1 volts at the bottom. And
so 2 minus 1.
2 minus 1, right? So
is 1 volt.
Yeah, we get 1 volt, but since it's operating
now, 1 volt, is it a positive or a negative number?
It's positive.
Since it's positive, this goes to full positive.
Right.
Okay. Okay, so let's try a different number. Let's assume that the voltage on this pin right now is 4 volts. Somebody else tell me what the Mohammed?
It will be 2 minus 4, so our output is negative, which will give us a 0 output.
Right, so we'll get a 0 on this. And the same thing's true of this one. Whatever the voltage in at this spot, 4 volts, is going to be compared against threshold. If threshold is bigger than 4 volts, positive comes out. If threshold is smaller than 4 volts, 0 comes out. Notice that the pin itself, threshold and trigger, are hooked to different places. This one's hooked to the positive side. This one's hooked to the negative side. Same math goes on, but we treat which one is being compared a little bit differently. Let's assume for a moment that the same situation has occurred. We have 4 volts on trigger, and we have 4 volts on threshold. We know this guy is off. What's this guy going to be? Well, 4 volts minus 4 volts equals 0. Is 0 positive or is it negative? And the answer is we don't know. If they're ever exactly equal, it may go fully on and it may go fully off. It's very rare that it would ever be exactly the same. And I mean exactly down to the electron the same. So we don't have to worry about the 0 case. Yes, in theory, it has a third value, which could be, it would be completely off, which is a 0. In our case, that's fine. If it makes it a 0, that's the same as though the negative had been too big. But had we actually had the ability to go to negative values, then that could have been a problem. We just won't worry about it because in this case, it can't happen. But in the other cases, it never will happen. Okay, so that's going to handle what value is coming out here. Now, the next thing we don't know about is this box right here. This box is something called an RS latch. And the way it works is if you push the set button, its output becomes a 1. If you push a reset button, its output becomes a 0. If you keep pushing the set button, it stays a 1. If you keep pushing the reset button, it stays a 0. So once you set it or reset it, it won't change until the other thing is pushed. Pushing means we put a positive signal on it. So a positive on set will cause the output to be a 1. A positive on the threshold guy up here, which hits reset, is going to cause reset to be set. You would never push reset and set at the same time. However, the reset that's at the top up here overrides both of these. If it's ever taken to 0, the output is immediately taken to 0 and held there as long as reset is 0. If you release reset, whichever one of these is pressed will win, assuming both won't be pressed. If neither are pressed, you'll still be left at reset. Now, the output is not really 1 and 0. Notice in this case, it's inverted. So pushing set makes the real output become a 0. Pushing reset makes the real output become a 1. Kind of dumb, but it does. That is re-inverted by this inverter. Notice this is just an inverter with the bubble on its nose or on its tail instead of its nose. So the output out here is exactly the same as what we would have had on this. So if there's a 1 here, it comes out a 0, gets re-inverted to a 1. So the output out here matches whatever set and reset said to do. They are the internal value, not the external value. Now that's all nice and handy because if the value here ever becomes a 1, which means this and that are a 0, right? Then this transistor has a 1 on its base. A 1 on its base is going to be a voltage high enough to allow current to flow through and turn the transistor on. If the transistor is turned on, then if anything is hooked to discharge, it will discharge to ground. If, however, what we have here is a 0, 0 will cause the base to be grounded, the same as the emitter, meaning no current will flow, meaning discharge will not be allowed to pass anything through the transistor. So we know a few things. Even though we don't know how it all works, we know the tools we have. We have the ability to turn this transistor on and off using our latch, which has a set and a reset. If we say set, we're going to turn off the transistor because the output would be a 0. If we say reset, we're going to turn on the transistor. Of course, transistor being on means if anything is on discharge, it will discharge to ground. We know that the output is a re-inverted version of whatever the latch said. So if the output is on, it means the transistor is off. We also have these two comparators over here that are looking at the voltage on 2 pins. Top one's looking at threshold, bottom one's looking at trigger, and comparing it against whatever is on this voltage divider at the point where they're plugged in. The top one's looking at the 2/3 point, the bottom one's looking at the 1/3 point. Anybody have any questions about that internal diagram? Some people call it the infernal diagram. Okay. We'll download another file. Instead of any 555.pdf, stick an A after the last 5. I think that's what I want. Nope, that's not the name of it. Should be 555a.png. Yeah, it is the right name. So I just typed it wrong. It look like that. I'm going to open my own copy of it. And what we have here is the external view of the chip that's going to use that internal design. I want you just to cast your eyes upon it for a few minutes and look at it in conjunction with this picture. You know, look at it in conjunction with the other one. I don't know where the other one even is right now on my screen. Nope, with this one. So you can look at the internal view and the external view kind of at the same time. And try to figure out what all these names mean and why they're where they are. Now, the main thing we're going to do with this is we want to be able to generate a square wave. So we can use it as a clock in our sequential circuits that we're going to start studying next time. Now, the amount of time from a falling edge to a falling edge, or from a rising edge to a rising edge, is called the period. It's measured in seconds, and it's the inverse of the frequency. So the frequency of this, let's say it were 100 times a second. I had 100 times a second. That's my frequency. If I invert that, that tells me how long the period is. The period is 10 milliseconds long. The next thing we need to know is there's an off time and there's an on time. The relationship of the on to the off time, time on over time off. I'm sorry, I'm going to do that opposite, put off on top. Time off over the total time is basically the time we have where the thing is going to be off. These two add up to each other. So the time on with respect to this is a percentage of time on, percentage of time off. We call the relative time the duty cycle. I don't know if I can type on this or not. That's the on time to the off time. So if we're on for 50 or 40, let's go 60% and off for 40%. The duty cycle of that is 60% because we're on 60%. It's always relative to the on time. The off time, add them up, we get our 100, whatever these were, units that it's going to be relative to. We're going to be concerned about setting the amount of on time and setting the amount of off time to equal the period so we can invert it to get the frequency we might want to have to use. We're working here when we do this with something which is called an astable multivibrator. And when we look at our diagram here, we see very little clue that that's what's going to happen unless you have a trained eye. But some of the ideas behind this will be really simple to talk about, and then we'll go into some depth on the next class after you've had a chance to be able to study it. First of all, let's look at some of the, you know what I should be able to do? I don't know if I can or not. I guess I can. Let's look where VCC externally is hooked up. So the external VCC is hooked to a resistor to the positive side of an LED to ground to the output pin. That means that we're wanting to light up the LED here when the output signal is low. This part from here to there could be most anything. It's whatever you want to deal with. That's your load. This is the resistance of the load. This is the diode, which we happen to be lighting up. We could turn this around, and then it would light up when this was high, but then we'd have to make sure that this was at a lower level like ground. We'd probably hook it down here. Notice ground simply goes to ground. In our other circuit, remember, ground is hooked to the transistor and to the bottom of the tree. So I think I have it. No, I don't have it up here anymore. Here it is. It's hooked to the bottom of the tree, and it's hooked over here to the transistor's base emitter. Now, pin 5 is simply tied through a capacitor to ground. Not going to explain why this is done, but this particular one is called a bypass capacitor, as is this one. Their entire purpose is to cut down on the amount of noise that makes it into pin 5 or into pin 8. Notice that VCC is also hooked to reset, meaning that in the circuit we're building, it's going to hold this pin high, so this pin does nothing. It's tied high, so we can't make it change. So we don't allow a reset. We have to power it off and power it on again. We're also tied to the top of the tree. How do I know that? Well, I see what's going on here, and I can see that this is hooked to that discharge pin and to the trigger pin. So while it's not hooked to this part of the tree externally, internally it is, we're also hooking ourselves, I can't reduce that very easily, to this threshold pin and trigger pin indirectly. Okay, now what's he mean by indirectly? He means that we've got some extra resistors in here before we get to ground. So apparently we're taking this internal tree that we can't see the hookup from 5 to ground, but it is from here to ground. And externally, we're building a secondary tree where A and B don't have the same values that those internal resistors did. And it's sitting on top of what looks like a big fat capacitor down here. Okay, that sounds good. We know capacitors have a charge and a discharge time associated with them. We may be getting somewhere if we can control how fast this takes to charge or discharge. Now, let's move ahead. We have the discharge value hooked to the top of resistor B, and we know we can open and close that by manipulating that set reset value we have in there. So the latch can let us turn this on or turn this off. We also know that threshold and trigger look like here we're measuring the same spot, which is how much voltage there currently is on top of the capacitor. But remember, one of these goes to 2/3 and one of these goes to 1/3 in the tree from comparison. They go to separate comparators. So we must be going to do different things depending on what the value is on the capacitor. Okay, let me just talk you through what's going to go on without explaining the technical detail and see if you can kind of pick up on what's going on here. When we first turn this circuit on, the capacitor is going to have 0 volts on top of it. Because it has 0 volts, that means at the trigger, we're comparing 0 volts to a spot which was 1/3 of the way up to the power supply. We'll pretend like it's still 6 volts, so that would be at 2 volts. That means that bottom relay, do I have it still open somewhere? No, I don't. The bottom relay is going to have, yes, I do. Bottom relay is going to have 2 volts on it, which is positive, which means he's pushing the set button. If he's pushing set, that means output is high, this is low, the transistor is turned off. So if the transistor is turned off, let me see if I can grab a corner of that window somewhere. That means that discharge is turned off, the transistor is turned off, and this wire right here is basically ineffective. So we have voltage coming in through resistor A and B trying to charge the capacitor. So the voltage on the capacitor is starting to rise. When it passes the trigger value, the bottom one, when it passes that value, it'll stop pushing this button. But it won't matter since we didn't push reset. This will keep the transistor off and make output be turned on. The capacitor charges, keeps charging until it gets up to, in our case, 4 volts. At 4 volts, we're going to measure 4 volts here. The threshold is going to be equal to the value we're measuring. And then it's going to pass it slightly, and it's going to push the button right here. Reset will occur. Because it's reset, this will go high, the output will go low, transistor will turn on, discharge will turn on. Once discharge turns on, the voltage on top of the capacitor now has a way to start dropping again. And it'll start discharging until it has dropped back down to the point where it matches the trigger voltage, at which point we turn discharge off again through that latch, at which point we'll start charging the capacitor up again. So what we can see is the capacitor is getting charged through both resistors. Then when we get to the 2/3 value, it starts becoming discharged, passing through only one of the 2 capacitors. Now, while we're charging, the output is high. Meaning, since we're charging through 2 resistors, the high value is going to be longer than the discharge when it's low value. So we're always going to have a duty cycle that is bigger than 50%. Because we charge through A and B, and we only discharge through B. We'll charge after the very first time, anytime we get to the 1/3 voltage, and we'll discharge anytime we get to the 2/3 voltage. And we'll basically cycle back and forth, causing the output to go back and forth between full on and full off every time we have a direction switch of charging and discharging the capacitor. Now you might say, let me go back to the data sheet, which was here. No, it was here. No, it was neither of those. I think it was online. Yes. And what we're going to see is, I think I have to go to page 11. Here's our astable operation. We're going to see that while we're high on the output, we'll be charging. While it's low, we'll be discharging. And you can study this. Here's a diagram we were just looking at with the external components added on it. And if we look at this carefully, we'll see a bunch of formulas for determining when we're on and when we're off. So the time high is determined by multiplying 0.693 times the resistance of A plus B times the capacitance. This time we get right here is using only a portion of the discharge. You remember our time constant chart was the amount of time it took to go from 0 to 100%. What they've done here is calculate how much tau is necessary to go from 33% to 67%. And it's 0.693 tau times our resistor times C. And since the charging time is through 2 resistors and the discharging time is through 1, these won't be the same time. The period, here's how you calculate the time high plus the time low. Here's how you calculate the frequency. These are basically the same number. One is inverted because one is the driver and one is the internal value. You'll figure out which of those to use. And then this is basically the low to high ratio, which helps us calculate the other values. Now, we have an equation with 3 unknowns, sometimes 4. What frequency do we want it to oscillate at? What value C should be? What should RA and what should RB be? Here's a chart which will help with this. Here's the frequency you're trying to obtain. Here's the capacitance, and these tend to be the useful capacitance you might use. Then the diagonal lines give you the value of the sum of the charge and the discharge resistors. So it's A plus B plus B. And you can pick a spot. So if we wanted to operate at 1K and we wanted to use a 1 microfarad capacitor, the closest line here is this line right here, which says we should get our RA plus our 2 RB to equal approximately 1 kilo ohm. And you'd want to size them so that A was significantly smaller if you wanted a 50% or close to it duty cycle. We can't achieve the duty cycle of 50% with this design because we have a different high and low set of resistors. And since this always includes B and this always includes B, the high value is going to always include an extra resistor. Smaller we get, the better, but if we get too small, we'll have too much current flowing, and really we won't get what we're expecting. So that little section on page 11 there, and it overflows 1 or 2 lines, is worth running your eyeballs over for our class on Wednesday night. Does anybody have any questions? You'll need to read through this and get a good understanding of the thing. Now, prior to that, up here, we have what's called monostable operation. This simply, upon hitting trigger, causes it to come on for a duration of time and going off. This is a useful circuit too, but we're specifically looking at the one that starts on page 11 here, the astable operation in 8.3.2. So make sure you can work through talking about how this operates. So when we need to use one with a flip-flop next class, you'll know what to do. Any questions? And let me see if my watch matches the clock on the wall, because if it does, we're done for the night. And it does indeed. So I shall see you fine folk on Wednesday, unless I see you first in some other class. So you all have a nice night. And to them, make sure you spend some time on this. Don't just come to class and think you're hiding in the background. You're not. You're losing points for not participating. But I can't make you participate any other way than encouraging you. So maybe we'll start not having you raise your hand. Maybe I'll just start calling on people. Okay, good night. Tell me good night and be gone if you need to be.
Have a good night.
Good night.
Good night, Professor.
Good night, Professor.
Professor.
Bye-bye. Bye-bye.
Good night, Professor.
Good
Good
night.
night, Professor.